Hello everybody, this is Professor Halsey, and today we're going to be looking at work and energy. Okay, you have a box with a mass of 40 tons pushed on a horizontal force of 150 newtons. Notice it's being pushed straight in the middle of the box. The box moves at a constant speed across a level plane at a distance of 6.55 meters. What's the work done? Okay, well, to determine the work done by the applied force, we're going to take the force times the change in the x direction, which means how far did it move, times the cosine of the angle that it was pushed at. It was pushed at a 0-degree angle, so that would make that the cosine of 0. Okay, so we have the 150 newtons that was applied, and the change in x direction was 6.55 meters. That gives us 983 joules. Okay, and B wants to know the coefficient of kinetic between the box and the plane. So from Newton's second law, they derived these formulas and come down, and then what we have is the sum of the forces in the y direction is equal to the normal force minus the mass times the gravity. It's all equal to 0, and then we can solve for the normal force by multiplying the mass of the box times g, 9.8 meters per second squared. So 4.2 times 9.8 gave us the 412 newtons. We can then use our coefficient of static friction is equal to the kinetic friction divided by the normal force. So we had the applied force of 150 newtons. And then the calculated friction, the normal force here. And we divide those two together and we get the coefficient of static, or the kinetic friction. Okay, the box of mass 2.5 kilograms is pushed 2.6 meters along a frictionless table. This time it has a force of 17 newtons. It's directed at an angle of 25 degrees. So we use the same equation, but this time it won't be cosine of 0. Okay, so we want the work done by the applied force, normal force by the table, and the work done by the force of gravity, and the work done by the net force of light. Well, one at a time. The work done by the applied force, again, the same formula we looked at in the last problem. The applied force, 17 newtons at a cosine of 25 degrees. And it moves 2.6 meters. Okay. For B, the normal force is at 90 degrees, at a 90-degree angle. So that gives us 0. And the work done by the force of gravity, again, the angle is 0 or 90 degrees. So that would give us 0. And then the net force, we add them all together. 0 plus 0 plus 40.1. All right. Number 3, a mechanic pushes 3 times 10 to the third kilogram car from rest to a speed of v doing 5,220 joules of work in the process. During this time, the car moves 26 meters, neglecting friction between the car and the road. Find V and the vertical force exerted on the car. A, the speed in meters per second, and B, the horizontal force exerted on the car in newtons. All right. So we use the work energy theorem, and the net energy is equal to the final energy minus the initial energy times K. All right, in this case, the net was 5,220. Okay, and that's going to be set equal to 1/2 mv squared minus 0 because it started at rest. And we solve for V. Okay, second, I'm trying to make sure this is going to work. We have work alright, there we go, equals, it's not doing great, 1/2 mv squared. Okay, so let's make sure we know how to derive this equation. Work, let's see if I can get it going, work equals 1/2 times m times v squared. Okay, so to get the half off of the right side, we'll multiply through by 2. So 2 times w would then equal m times v squared. Okay, so then to get m off of the right side, we divide through by m, so it'd be 2 times w divided by m now equals v squared. So then we take the square root of both sides, 2 times w divided by m, take the square root of that, and it gives you v. Okay, a 16 kilogram base runner begins its slide into second base when he is moving at a speed of 3.8 meters per second. The coefficient of friction between his clothes and earth is 0.70. He slides so that his speed is 0 just as much as the base. Much mechanical energy is lost to friction acting on the runner. And how far does he slide? Okay, so let's look at the work that's done is 1/2 mv squared final minus 1/2 mv squared initial. So just like the last problem, only now our initial is not 0. His initial velocity, he begins his slide at 3.8. Final velocity, however, is 0. So we end up with negative 1/2 mv squared. And we're solving for the work, so we don't have to change the equation. Okay, so 1/2 times the mass times 3.8 squared. And the energy loss is 498. Do not put in the negative sign. Now we want to determine how far he slides in meters. Okay, so first we can use the work equals force times the cosine of the angle times the distance. Here they're using S for distance. And to solve for the distance, we transpose the equation and we end up with negative W divided by the coefficient of kinetic friction times mass times the gravity. Okay, we just calculated the 490 joules. We divide that by the 0.7 that was given for the coefficient of friction times the mass that was given for the runner times 9.8. And that gives us a distance of 1.05 meters, just over 3 feet. A man pushing a crate has a mass of 92 kilograms at a speed of 0.860 meters per second. He encounters a rough horizontal surface of length L. It's 0.65 meters, as in the figure below. Okay, so this is the rough here of distance L. If the coefficient of kinetic friction between the crate and the rough surface is 0.354 and he exerts a constant horizontal force of 284 newtons on the crate, find the magnitude and direction of the net force on what's on the rough surface. Okay, well, let's look at that part first and then we'll move to the next part. The crate has 0 vertical acceleration, so the sum of the forces in the y direction is equal to the normal force minus mass times gravity. Now that's set equal to 0, and the normal force is equal to mass times gravity. Thus the kinetic friction force is Fk, or the coefficient of friction in the normal, equals the coefficient of the kinetic friction times the mass times the gravity. All right. Note that the two vertical forces acting on the crate cancel, meaning that the net force on the crate is horizontal. So it's not moving up and down, it's moving only sideways. Choosing the x direction toward the right, we have the sum of the net forces is the applied force minus the coefficient of friction, or using that formula we determined up here, that coefficient times mass times gravity. Okay, so we take the 284 newtons that he exerts on the crate minus, and then we take that coefficient times the mass, 9.2 kilograms times 9.8. Since it comes out negative, that means it's in the opposite, it's in the direction opposite of the motion of the crate. For B, find the net work done on the crate while it's on the rough surface. So the work is the force times the distance times the sine of the angle. We found the net force here. The change in the x direction was given as L, 0.65 meters, and the cosine of 180 degrees, because we're looking for the work done on the rough surface. Okay, for C, we're looking for the speed of the crate when it reaches the end of the rough surface. So we can use the net work to determine the velocity using mv squared, 1/2 m, the final velocity squared minus the initial velocity squared, and they actually show us how to derive that here. So we take the square root of 2 times the net work that was determined, divided by the mass that was given, plus the velocity given at 0.86 meters per second. Use 0.86 squared plus that value, and then take the square root of that. And the figure below shows a motorcycle leaving the end of the ramp with a speed of 34.9 meters per second and following the curved path shown. At the peak of the path, a maximum height h. At the top of the ramp, the motorcycle's speed is 33 meters per second. What is the maximum height? Ignore friction and air resistance, and your answer should be in meters. Right, so while the motorcycle is in the air, only the conservative gravitational forces act on the cycle and the rider, therefore 1/2 mv final. Velocity squared plus the mass times the gravity times the velocity in the y direction. So we derive that, and the height is going to be y final minus y initial. So to find y, I don't know why they wrote it that way. It's kind of, okay, weird. So we use the initial velocity squared minus the final velocity squared. I was going to say, this is the formula we've been using all along. I don't know why they went with this. No, here we're using gravity, and so this is the 1/2. All right. Anyway, the initial velocity was 34.9 meters per second. His final velocity at that height was 33 meters per second. So we square both those numbers and subtract them from each other. So 34.9 squared minus 33 squared. And then we divide that by 2 times 9.8. A block of mass 32 kilograms pushed against a horizontal spring of a constant K, 785 Newton meters, and pushed so the spring compresses by 0.055 meters. What's the elastic potential energy of the block spring system in joules? Okay, so the potential energy of the system is 1/2 times K times x squared. So 1/2 times the K that was given, the spring constant, times the distance it was compressed squared, and we get 1.19 joules. If the block is now released and the surface is frictionless, calculate the block's speed after leaving the spring in meters per second. Okay, so the kinetic energy plus the potential energy of the spring plus the potential energy of gravity, and I'm not sure initial and final. So we use the kinetic energy to start with is 0, the potential due to gravity 0. So this is moving in the x direction, it is not moving in the y direction. And the potential energy of the spring, 1/2 times the constant times the distance squared. Now the kinetic energy on the other side is 1/2 mv squared plus, and again, gravity 0 effect, and on this side the spring has no effect. It's already sprung. Okay, so we derive that formula, and to find the velocity we have to take the square root of the constant divided by the mass times the absolute value of the distance that it moved. Okay, so the constant 785 newton meters divided by the 3.2 kilograms that was given times, so you take the square root of that first and then multiply that by 0.0550. Okay, and our answer is in meters per second. 55 kilogram pole vaulter running at 10 meters per second vaults over the bar. Her speed when she is above the bar is 1.2 meters per second. Neglect air resistance as well as any energy absorbed by the pole and determine her altitude as she crosses the bar. That would be her height. In the y direction, so our y final. So we have 1/2 mv squared final plus the mass times the gravity times the y final equals 1/2 mv squared initial plus 0, because the initial point was 0. Okay, so we can solve that to find y final, or distance in the horizontal direction. How high did she go? Using the initial velocity squared minus the final velocity squared times 2 times gravity. So pretty much like we did in the last one, we're looking at the initial velocity squared, 10 squared, minus the final velocity, 1.2 squared, and then divide that by 2 times 9.8. That gives us our answer in meters. If you have any questions on Module 3, let me know. Thank you.